So while the next last talk of the day is getting set up, quick question for everyone. How many founders, co-founders in the audience? Okay. How many of y'all, actually y'all should stand up because people want to look at you because you're potential employers. All right. Of the founders, please stand up. I'm also standing up. I'm also a founder. Are y'all still coding? Are y'all still coding? And yeah, and that's a good sign, right? Because our next speaker, Chinmay, is one among y'all. It's always good to have a founder who codes. And he's given me specific instructions. Don't tell anyone about my talk. So I have absolutely no idea what's in your mind. But Chinmay, go for it. Over to you.
Check. Perfect. All right. Yes, I know you're waiting for the next after party and whatnot. So I'll keep this brief. This is the last talk. So I want to run an experiment. I don't want you to look at the schedule and guess the title of the talk and find out. Let's try to decrypt it, right? The title of my talk is quite mouthful, so I've decided to emojify that a bit. What do you think is this image? There's a specific name for this. It's called Goldberg machine, Rube Goldberg machine, right? What do you think is this? So it's almost like a big ball of spaghetti in a marshy terrain, right? What has that got to do with Ruby programming, etc.? Right? So the first is an example of an over-engineered system. What's the purpose of Goldberg machine? Well, ultimately, it just presses a button or it triggers a switch. So why have this complicated machinery to just click a button, right? And on the other side, we have a big ball of mud. So the title is Don't Do Over-Engineering and Avoid Big Ball of Mud. I want to talk about the 7 lessons that I've learned for maintaining the balance. All right, this is me on GitHub, Twitter, or whatever it is called these days, and LinkedIn and other social media. A bit about me. Gautam talked about, I'm a founder at One2N, where we focus on backend engineering and site reliability engineering. We help startups and scale-ups scale to new heights. Personally, I love engineering. I love psychology, percussion. I play tabla, and Age of Empires. Any Age of Empires fans here? Woo! Cool. We should probably play a game later, something like that. Okay, who here has seen this cartoon while growing up? Okay, yes, I was expecting that. So if you've seen this cartoon, then you probably are familiar with this episode where Tom is trying to build a better mousetrap. So like any ivory tower architect, what he does is goes into a room, gets to the whiteboard, starts designing the system. He has all the requirements, where Jerry's hide hole is, where to start from. He designs a perfectly aligned system with lots of components and whatnot. And then he works on it hours, days together, and then goes live to production. What do you think happens when he goes live to prod? He's obviously not managed to catch Jerry. Jerry fools him again. And like fundamentally, this is what happens when we over-engineer systems, right? We are not able to get them to do the simple thing that they were designed for. Compare that to something like this. Who here has played this game? Okay, a lot of you. This, in case you haven't, it's called Jenga. The idea is that you have a tower of blocks, and you have to remove one block at a time from middle of the tower, place it on top of the tower, while making sure that the tower doesn't fall. Like, that's the objective of the game. It's a multiplayer game. You play with 2, 3, whatever number of players, right? Over time, you end up with something like this. So compare that in software to a perfectly designed or perfectly theoretically perfect system where you have all the requirements written down and you have got a tower of Jenga. And now what happens is, like if you think about what's the most universal truth in software, that requirements change. And that's what happens. You keep on changing the requirements. Think of removing a block and placing it on top as changing the requirements, right? As you change requirements, you're going to end up with a tower that looks something like this. If you're not careful, and if you do that over long periods of time, entropy kicks in, and you are going to end up with a tower that falls, right? Like you try to make one small change in the system, and the whole thing topples over. This is an example of a big ball of mud kind of system is what I would call. So, recap. We've talked about two systems. On one side, there is overengineering, and on other, there is big ball of mud, right? The idea of good engineering is about balancing between these two. I've often seen teams fall either under overengineering side or on big ball of mud side. You know, on overengineering side, they think, hey, I can't write code until I know everything, and I have to think of all system components upfront. I have to think of designing the system such that it can cater to any change in future. You've probably heard about open-close principle, right? So idea is that you keep your code open for extension and closed for modification. Well, you can't have your code open for extension forever, right? Like you have to assume some things. So if you design your system for a lot of requirements, you're going to end up with an over-engineered system. On the other side, big ball of mud would be, let me just do one small patch and see what happens. I'll worry about scale, or I'll worry about refactoring later, right? If you do that over and over and over again, you're going to end up with a system that is very fragile and difficult to work with. So before we talk about how do we balance these, right? Let's talk about how these systems affect our day-to-day work. So think about how change could be handled. So you have an incoming new change. In case of over-engineered system, a simple change becomes super complex, right? And a complex change, well, almost impossible. In case of big ball of mud, you may start with a small fix, but that may result in something completely breaking the system on completely unrelated part. It's almost like you're trying to fix a boat with a duct tape, and you realize, oh, there's now a new hole, and I need to patch that as well, right? So how do we get to these systems, right? As you said, if you design a fully generic system upfront, which can cater to many possibilities, it can scale to this, it can scale to that, you can change this component, it'll still work and whatnot, you probably are overthinking. And if you have a too tightly coupled system where you can't even make change without changing any of the other components, then you're going to get, what you are working with is a big ball of mud. And if you do that over long periods of time, you get a big ball of mud. So what this results in for engineering teams is many unused features, right, and components. In order to set up just the system, you're going to have to set up the whole elephant, is what I call it. And on the other side, there is too much tight coupling with respect to components. So the fundamental thing is maintaining this balance, right? That's the key here. Like you don't want to fall on either side. You want to maintain a good balance so that you can build software that works for today and also can scale for tomorrow. So how do we do this balance? What I'm going to talk about is 7 lessons or principles or guidelines. These are definitely not like rules or dogma or universal truths that I want you to think about. Think of them as some guiding principles, if you will, that you can take home, think about, and apply this in your daily life. So I think I want to start with the first one, which is assemble software instead of building it from scratch. We often have a tendency to build everything ourselves as developers. We often want to solve all of these problems ourselves instead of looking for any existing solution in most cases. Think of car manufacturing, right? If you know any car manufacturers, like how they work, right? They don't they mostly outsource a lot of parts of car building to third parties and vendors. Even some parts in the engine are outsourced to third parties. So I'm not saying software engineering and car manufacturing are same industries. There's a lot of similarity, but we can learn a lot from these industry, right? So one thing that they get right is they assemble things together, right? What assembly gives you is that it lets you use predefined components, it lets you test out things in isolation, it lets you reuse somebody else's work and then iterate faster, right? So instead of building, for example, if you're building a CRUD app in Rails, don't go and build your own A/B testing framework, for example, right? Like use something like Split, for example. Or don't go designing your own background worker and fancy solution. Just probably start with Sidekick, if that makes sense. So years ago, I worked on an application where we were building a simple CRUD kind of application. And we were about like 15-member team. We worked on it for almost a year and a half, and we never went live. The reason, looking back, is one, we were doing something what is called as bike shedding, right? We had our ideas of what we want to build, and we started building things around that. So instead of using a tried and tested framework, we started writing our own custom routes and logic and whatnot to build our own, it's almost like scratching our own itch, right? But not doing any actual value-add user-specific work. So this is something we need to be constantly aware of and avoid this as much as possible, especially if you want to have this balance of good software architecture and design. So there is a really good advice or a framework that I have seen that I like, which is by Michael Pollan. He says, eat food, not too much, mostly plants. Similar to that, I want to say something like this for software. Build software, not too much, mostly core to your business, right? If you try to build things extraneous, you're probably solving a wrong problem, or you're probably wasting time where you could have used some existing solution. So to recap, we talked about why assembling software makes sense in some cases, obviously. Second thing I want to talk about is using proven and boring tech over a fancy, shiny new tech. So let me dig deep into that. Proven tech is something that has a predictable modes of failure, right? Something that you can rely on for it to work, and you can have your good night's sleep, right? You will know when things break. You will know when it can fail. It has more predictable modes of failure, essentially. Boring is, in a way, like it's been tried and tested for years, something that works for long periods of time without a lot of maintenance. Whereas, on the other hand, shiny tech is something that came up recently, where you can probably, like if you want to experiment with shiny tech, you should probably do this in a dev, non-prod kind of environment where you have lower blast radius for your work and experiment with it, right, before putting it out into production. So if you care for uptime and reliability, I think we have talks coming up tomorrow on that as well, and there were a few talks today as well. It is better to kind of use a proven tech that works and gives us peace of mind. So some examples of like what boring means in this context. Think relational databases, Linux commands. Think RAC, Rails CRUD conventions. These are super useful where if you learn these conventions once, then you're going to be able to rely on them to work consistently, and then changing across projects, work becomes much more easier. Whereas in case of Shiny, think something like this, where somebody claims to build a Shiny new authentication library that claims to change the world, whatever that means. Or a database which says, hey, store the data, I'll retrieve it 10x faster. No caveats. If you hear something like that, most likely people are trying to sell you something, so technology without any trade-off is hard. You should be thinking beyond the marketing gimmicks that is usually put out on the website and find out things from inside out, experiment with it, etc. All right. Third is building composable software. Composability is like Lego, where you assemble parts of Lego together to build a bigger, larger system, right? The good thing with Lego is that if you don't like one of the parts, you can swap it out completely. You can test parts of the system in isolation. As long as there is a consistent unified interface between these parts, they can be plugged together without any problem, right? So composability is not just with respect to Linux commands. That's where we usually think of it, and it comes from something like Unix philosophy. It's also with respect to data pipelines and open framework, open protocols, etc. So one example that I want to take, I'll promise you this is the only slide where I have a bit of Ruby code. So imagine you have a bunch of YAML files across multiple subdirectories, and each of these YAML files have a bunch of data in them, and it has a tags line where you can find tags, and these tags are comma separated. So think EDB, WordPress, WP, etc., right? These are comma separated things. What you want to do is across all of these files, across all folders, you want to find which are the 5 most common tags used across all these files. So this is what a Ruby program that you would end up with. You would start with something like which goes through and walks through all the YAML files in directory. You walk through them, you find the file names, you open the files, you grep for tags. Then you find out the string after the tags, right? So you're going to extract the string after the tags. You're going to split the white spaces if there are any. And now what you end up with is a string which, let's say, WP scan to 3D print. With that, you're going to reject any empty strings if there are any, and you're going to split that with a comma. And one really good feature in Ruby is that you can convert an array of strings or array of numbers, and you can just say tally, which will give you a frequency map, right? And then you can sort this by value in negative fashion so that you get the top frequencies first. And you just say, I want to take the first 5. This gives you so this is an example of a data pipeline where you have composability of functions which operate on a consistent data. In this case, it's an array of strings or array of numbers or stuff like that. Composability is not just for data, it's also for open protocols or frameworks, right? Think RAC, for example. RAC is so invisible that if you look at the RAC specification, you get a bunch of handlers, you get a bunch of middlewares, essentially. You can swap out a web framework or a web server as long as they're RAC compatible. So we talked about the 3 rules, or 3, I won't call them rules, 3 guidelines, 3 lessons. Let's talk about a 4th one, which is, we just had a talk on Kubernetes and deploying Rails applications. So it's very important to build systems that are operationally simple to maintain, right, and are predictable. Why? Because again, if you care about your night's sleep, then you want to run systems such that they run without a lot of maintenance, right? So some really good features that I like about Rails, Ruby, and bunch of like overall Ruby ecosystem in general is, for example, like Rails asset pipeline, which makes it very easy to compose a production-like artifact. If you want debuggability, you can do that on dev. It makes it very easy to change the configuration by just setting env variables like Rails env. It also has something like an API-only mode and a bunch of other functions. So this makes Rails a really good way to run it on production. Making maintainability as a first-class citizen and not as an afterthought. If you do that, your most of the team members will thank you, and you yourself will be able to operate the system that you built. This is almost like a product advice, not an engineering guideline or lesson. Especially from a 0 to 1 kind of journey, what I have seen is that building a product for one specific individual or one specific persona, instead of building it for the masses, all of them, really makes it easier to build that product and to be able to sell it and to have better success. So instead of solving some 1,000 people's problem in an average manner, if you can really solve a good chunk of someone's problem, make them more productive, make them a hero by solving their problems, and if you find 10 such users, they would be actually willing to pay you money, and you'll be able to build the product. So when you think of building systems, think for building for one specific user, one specific persona, and then think for building for similar set of users. It could be you would be able to cross-sell to them better, upsell to them better, etc. Right? And do this incrementally. From a consumer point of view, think choice fatigue is real. There's just so much software, there's so many tools, there's so many products out there that as a consumer it gets really overwhelming to find out, oh, you are same as that, or you are very similar to that. So how do I really distinguish and choose one software versus another, right? That's where going deep instead of going broad really helps. If you go deep into one of the areas and really solve that particular problem for the customer, you're most likely to succeed and make more out of it. All right, so we've talked about these 5 rules. I have 5 minutes remaining. So the next one is optimizing for speed of iteration. Here, again, the idea is that it is very difficult to know what to build. Building is the easy part, usually. That's what we have seen, especially in 0 to 1, right? It's very difficult to know what do we really build. And we keep thinking there must be something that I'm missing, which will tell me, which will give me an idea, what should I build, right? But because once we've figured out what to build, building that is much more easier then. But in reality, all of us have worked in various industries. We have seen it's very hard to know and understand user behavior and what really ticks, right? So instead, what we can do, what I suggest is we should try to optimize for mean time, like failure rate, and essentially optimize for the loop, which is the speed of iteration, where if you try out something and it doesn't work, you try and build something else and see if it sticks and learn from that, right? So optimizing for the speed of iteration than anything else would be a good way to think about it. Because let's be honest, we won't be able to build it right the first time. It's very hard, right? But we don't have to. That's where we can, this is almost goes into a bit of an agile like manifesto framework or summary of agile, which is you find out where you are, take a small step towards where you want to go as a goal, see if you're on the right path, evaluate, and then repeat, right? Keep doing this over good amount of periods of time, and you will have good system, and you will hopefully be able to solve the problem and focus on the right set of things. Lastly, I want to talk about something that's very important, which is all rules have context, right? Like there's a classic meme and saying that if you ask a senior engineer, what should I do? They always start with, it depends, right? Because it really depends on what you are trying to do, right? So all the rules that you will hear, somebody will say that, hey, use Kubernetes, or use microservices, or use monoliths, or Rails is slow or Ruby is slow, whatever. They're talking from their specific experiences or their biases. So you can't really apply any advice on the face value, right? Which is where you should not do what is called as cargo culting. Cargo culting is, I'm not sure if you are familiar, but there was a time in World War II where a bit of ingenious tribe would just do some rituals and assume that, okay, that was the ritual that made the planes drop the cargo from the air, right? So it's almost like small kids doing something that their parents do without realizing what it's meant for. Also, there is a really good, interesting paper by Fred Brooks. This is from 1986, almost same time as I was born. So it's called No Silver Bullet. It's a really useful paper which says that there is no single methodology, single architecture, single tool, single language that can claim to do 10x and that can claim to solve all of your problems. I would highly recommend, if you haven't looked at this, have a look at that paper. Summarizing the 7 rules here: assemble software instead of building from scratch as much as possible. Use proven tech that can work on production and let you sleep well at night while experimenting on staging, dev, using your shiny tech. Build software that composes well with each other and you can build big systems out of. To be able to build big systems, ensure that you are running things simple, lean, and keep them predictable. Building for something is not itself sufficient. What you build for, who you build for, that's where think about building for one specific persona, then expand for the next, and then do that incrementally, and optimize for this iteration speed, and know that all rules are contextual, don't apply using dogma or take things at face value. Thank you.
Wow, thank you, Chinmay. Any questions for point number 8?
When is the party?
Any questions for the point number 8 or something? No? All right. So thanks, Chinmay. Thanks a lot for your talk. And loud round of applause for him, please.